This question is on optimisation. It's practical applications of differentiation. The question is that I have an open square-based box of volume 4 litres. Now it's square-based, which means that these dimensions on the bottom are the same. I've called them x. You can call them whatever letter you want. However, the height is different, so I've called it a different letter. It's open, meaning that there's no lid. Really important when we come onto surface area. What I want to do is I want to minimise the surface area of the box. I want to find the dimensions that minimises the surface area. Now, to do that, I'm going to first of all use the fact that the volume is 4 litres, or 4,000 centimetres cubed. My units are going to be in centimetres, therefore I change the 4 litres into 4,000 centimetres cubed. The volume of any box is like this. Now what I've done is I've found a relationship between x and y. So when I come to look at just the surface area, if I substitute this in for y, it will give me an equation in just one variable, in just x. So that's what I'm going to do. I'm going to find an equation for the surface area. I have the base, and I have 4 sides, but I don't have the lid. Now if I substitute this in for y, it gives me x squared plus 4x like this. What you can see is I have an equation solely in x. Here I couldn't differentiate it because I had 2 separate variables, x and y. But now I have an equation just in x. So this means I can differentiate it. dA by dx. I can find how the surface area changes with respect to solely the base. So if I differentiate this, I get 2x minus 16,000 over x squared. Now I want to find the minimum point. That's a turning point. Same if I wanted to find a maximum. What I do is I find the turning point. So I find out where it's equal to 0. If you rearrange this, you get 2x cubed equals 16,000. Solve it for x equals 20. But I don't know if that's a maximum or a minimum. So what I'm going to do is I'm going to do a sign diagram for dA by dx. Now, if I do this is a primed, or dA by dx, there's a turning point at 20. If I let x equal, for example, 10, I would get 20 minus 16,000 over 10 squared. That gives you minus 140. So therefore, when if x equals 10, a primed is negative 140, i.e. it's a negative gradient. Okay? So a primed is negative here. Given it's a turning point, you know that it's a positive here. Okay? You could also put in a value, take x being 200 billion. This is huge and this is very, very small. Therefore, a primed will be positive. So I know that my graph looks something like this. Yeah, that's for a, not a primed. And it's therefore a minimum. X equals 20 is a turning point and it minimises the surface area. Okay? If I find y equals 4,000 over x squared, that would equal 10. Therefore, x equals 20, y equals 10. The dimensions of the box are 20 by 20 by 10. If you didn't want to do the sign diagram for a primed, you don't have to. You can also differentiate this again. If you differentiate this again, you get d squared a by dx squared. You have 2 minus plus times by the 2, 32,000 over x cubed. If you substitute in any value whatsoever into this, you get it being larger than 0, if x is larger than 0. Therefore, because d squared a by dx squared is larger than 0, that also means that any turning point is a minimum. And therefore we have proved that these dimensions minimises the surface area of the box.